In this lecture series, we'll be learning about resonance structures. In this first video of the series, we'll learn what resonance structures are and how to draw them. Let's start with acetate. When I drew acetate here, I chose to put the double bond on one oxygen and the three lone pairs and the charge on the other oxygen. But I could have drawn it the other way. I could have instead put the three lone pairs and the negative charge on the top oxygen and the double bond to the bottom oxygen. These two different depictions of acetate are resonance structures. They are partial descriptions of the true structure. And we can think of the true structure of acetate as a weighted average of the resonance structures. And it's important to remember that there is only one true structure. It's not that acetate is hopping back and forth or interconverting between these structures. There's one single structure of acetate, and each of these resonance structures is an incomplete description of that structure. Another super important thing to note is that resonance structures differ only in the placement of pi bonding and non-bonding valence electrons. We will never break or form a sigma bond when we draw a resonance structure. Finally, we use curved arrows to show the flow of electrons that relate to resonance structures. The curved arrows begin at the origin of the electrons and end with the arrowhead at the destination of those electrons. So in this depiction, if I want to draw the resonance structure of the acetate on the left, I would think about moving a lone pair on the anionic oxygen to form a new pi bond with the carbon. And when I do that, I give carbon too many bonds, so I have to also move the electrons in the existing carbon-oxygen pi bond onto the oxygen, giving the top oxygen now three lone pairs and a negative charge. I can also think about drawing the resonance structure of the acetate on the right, and that's the exact same movements in reverse than they're indicated here in red. Benzene is another common structure that has resonance or resonance structures. In this case, the electrons in the pi bonds of the ring can each move one position over to form a new pi bond on the adjacent carbon-carbon bond, giving us the resonance structure shown on the right. The two resonance forms of benzene are equivalent, but some structures have resonance structures that are inequivalent. The second example here will illustrate that for us. If we want to try to draw a resonance structure of this species, we should look at the lone pairs and pi bonds. And more often than not, if a molecule has a charge, then we'll consider moving those electrons to achieve a new resonance structure. So here, remember that the negative charge on the carbon means that the carbon is a carbanion. It has three hydrogens bonded to it and a lone pair. So we can move that lone pair to form a new carbon-carbon pi bond. Then we move the electrons in the carbon-oxygen pi bonds to the oxygen, giving the oxygen three lone pairs and a negative charge. Okay, this gives us the resonance structure shown on the right. And here you might wonder why we needed to move the electrons from the pi bond to the oxygen. And you might have considered stopping after you moved the first lone pair to form a pi bond. But if we look at that structure, we find that it leaves us a carbon that has 5 bonds. And when I was a student, my professors called that a Texas carbon, because everything's bigger in Texas, so only in Texas can carbon accommodate 5 bonds. We're not in Texas, and carbon only forms 4 bonds, so when you catch yourself drawing something like that, look for another lone pair or pi bond that can be moved in order to accommodate the valency of carbon. Okay, so in general, when we want to identify a resonance structure, we're going to look for an electron deficient or electronegative atom next to a pi bond. Here we had an oxygen pi bonded to a carbon. Right? Or alternatively, we'll look for a lone pair next to a pi bond. And that's exactly the case we had here. Now, looking at these two resonance structures, it's pretty clear that these resonance structures are very different. And now in this case, these resonance structures will no longer be equally weighted or equally favorable. Now one resonance structure will be more favorable or more heavily weighted than the other. And that's what we'll talk about in the next video of this series. Before we get there, let's stop for a concept check. Using the guidelines on the previous slide, determine if each of the following molecules has a resonance structure. Okay, in the first case, we don't have either of the situations described on the previous slide. And if we think, oh, oxygen has a lone pair, so I can form a new pi bond. Well, when you try to do that, you get only Texas carbons. So there's no resonance structures of this first molecule. In the second case, there is. I see a lone pair next to a pi bond, so I can move the lone pair to form a new pi bond, and then I can move the existing pi bond to form a new lone pair on the terminal carbon. In this third example, although I have a lone pair and a pi bond in the same molecule, they're not next to each other. So there's nowhere I can move the lone pair to create a resonance structure. So there are no resonance structures here. In the last case, I have an electronegative atom next to a pi bond. So I can move electrons from the pi bond to the electronegative atom. And this creates a valid resonance structure, but it's not a great resonance structure, as we'll see in the next video.